Welcome to Lesson 44 on Anonymous Methods Part 2. Part 2 will cover partial function application and how it can be used in Delphi. Partial function application can be a difficult concept to grasp. So before we delve into looking at how partial function application can be done in Delphi, I want to consider an analogous situation which might be more familiar, and because it's more familiar, might be able to communicate what is actually meant by partial function application better than if we jump directly into programming in Delphi a partial function application. The analogous situation is a radio. A radio can be viewed as a partially applicable function or partial function. A radio's main function is to transform electromagnetic or radio waves into sound waves. But before listening to a radio broadcast, a radio station is selected by frequency, for example 101 megahertz. In itself, the radio is quite a general function with many different broadcast frequencies to choose from. Hence, the radio first takes a radio station frequency as argument, and then the radio waves to be transformed. By selecting a specific broadcast frequency, the radio's function is specialized into one dedicated to transforming electromagnetic waves for this particular frequency. For example, if we've selected the station frequency 101 megahertz, then the radio is now a more specialized function which transforms electromagnetic waves into sound waves. So we still have a function, but it's a specialized one. So a partially applicable function is a function that, given its first argument, returns a new, more specialized function. If you supply this new function with an argument, you get the final result. This is what is meant by partial function application. So in reality, it really means you don't have to pass all the arguments to a function at once. In the example that we consider next, a function moves from being a two-argument function to being a one-argument, more specialized function. The function application of the original function is applied to just one of its arguments, station frequency, but not both. So in general, in partial function application, the function application of the original function is applied to just some of its arguments, but not all. So if we use partial function application notation, the original function can be described as station frequency, forward arrow, electromagnetic waves, forward arrow, sound waves. So this is the original function. Now if we supply the station frequency argument, we now have a partial function which is described in partial function application notation as electromagnetic waves, forward arrow, sound waves. So this is an example of a general principle. Any function taking two or more arguments can be partially applied to one or more arguments. So in the next example, we're going to consider the function add, which adds together two integer arguments and returns an integer result. We can write it as add xy equals x plus y. And in a black box display it would be x, y input parameters and the function add, giving a single output result. This function takes a pair of integers x and y and returns an integer. So in function application notation we would write this as integer forward arrow, integer forward arrow, integer. So this represents the input and this represents the output. If we apply the function to two arguments, the result is a number. So if the two input arguments are values 2 and 3, then the output is 5. But what happens if add is applied to one argument? So if we supply the value 2, but we don't supply a value yet for the argument y, what do we get out? Well, the output of this function application to one argument is actually another function of a more specialized nature. This time a function add 2 with one argument y. This new function will return 2 plus y, and this new function add 2 maps an integer to an integer. So in the notation that we've used for describing functions, it's integer forward arrow integer, input output. Well, let's try a Pascal ABC.NET example of a partial function application. So if we create a variable whose type is an anonymous function which takes two integer arguments and returns an integer result. If the two arguments are x and y, then this anonymous function returns x plus y. Now, partial function f applied to 2 is a specialized function which takes a single argument and returns a new function which adds 2 to y, i.e. it returns 2 plus y. We can now apply the partial function f2 to argument 6, writing it as call f open bracket 2 close bracket open bracket 6 close bracket and get 8 returned. So let's just have a look at this in Pascal ABC.NET. So the variable f is a function with two arguments of type integer and a result type of type integer. If we apply f to 2, we create a specialized function that will add 2 to y. If we specify a second argument here, 6, that will be bound to y. So the result return should be 2 plus 6, which is 8, which WriteLine will write out to this output window when the program runs. So let's run the program. And indeed, it outputs 8. If we change the specialized function to, let's say, 10, so 10 is bound to x and replaces x here in this expression. 6 will be bound to y, so we expect the answer 16, which is indeed what we get. Let's now take a look at what partial function application looks like in Delphi with the program Delphi Add to Project. So this is a console application. I've created a function type type t function of integer using the keyword reference, the keyword to, and the keyword function. It takes one parameter of type integer and it returns a value of data type integer. Now there is a built-in generic type called tfunc, which I could have used in place of all of this. So I could have said t function of integer equals tfunc integer integer. This name here is actually unimportant. What is important is the data type here. Now I've declared an ordinary function with name f, which takes a single integer argument and returns a function type t function of integer. Returned a t function of integer data type value. At this point we define an anonymous function. It's an unnamed function with the keyword function. It has a single integer argument and it returns a value of data type integer. And this function performs addition. It adds x to y. Now parameter x is not in this interface here. It's not a local variable here. So it's actually the x that is defined here. So it comes, so x here comes from the block which surrounds the anonymous function. So inside the anonymous function, x is known as a free variable, because if we just constrain ourselves to this function here, we cannot see where x has been declared or where x is a formal parameter. So we don't know at this point what it's going to be bound to. On the other hand, y can be linked to the y in this interface here. So we say that y is a bound variable because it's going to be bound to the argument that is supplied when this function is called. So the key thing here is that the anonymous function has to bind the free variable x to the surrounding lexical environment. Now in Pascal, variables declared in an outer block are visible inside or in an inner block. So the inner block is this function begin end. Okay, so just remind you again, an anonymous function is a special kind of first class function that is declared in line without naming it. This program again shows this program shows an example of how an anonymous function is declared. I've covered this here. Let me just remind you again that function f is a single argument function which returns a reference to a function of a single argument. Okay, so looking at the main begin end block, we can call f with the argument 2. It's a single argument function, but what is returned is another function of a single argument, and this inner function or anonymous function returns an integer result. So we create this specialized function f2 and then we apply it to the value 6. So 2 is bound to x at this point here, which is now visible and bound to this free variable here, x. And 6, because we're now running this function, is bound to y here, and therefore this y here is replaced by 6. So we have 2 plus 6, which is the result 8. And because this function returns an integer result, we can supply as an argument to WriteLine, so that WriteLine can write the result out to the screen. Okay, so next we need to run this program and demonstrate that indeed we get 8 as a result of running this program. Here we are in the IDE for Delphi 10.4. I have loaded the program Delphi add to project, and it is as described in the previous slide, with a function type, t function of integer, a function f, which is a single argument function which returns a result of t function of integer, which is the function type, so it returns a function, and the function which it returns is an anonymous function, a single integer argument, which returns an integer result. And we've got binding here of x to the argument supplied when we call f with value 2, and we've got binding here when we call the anonymous function with argument 6. So without further ado, let's run it and see what we get. And there you are, the answer 8. So if we were to change this to 4, so now we have a specialized function that will add 4 to the argument supplied here. So that will give us 6 plus 4, 10. And indeed we get value 10. Now what we have gathered from exploring partial function application is that we can reduce a 2-input function to a more specialized single input function. If we look at the function types, when we have a 2-argument function, we express the input using this notation, and when we have reduced this to the more specialized single argument input, then this becomes, in function type notation, integer forward arrow integer. So if you reflect backwards on this, you can see if you start with a single argument function and you want to turn it into a 2-argument function, then all you need to do is to add an integer forward arrow before the notation for the single argument function. Because what we've demonstrated is if you work in the forward direction by supplying an actual argument for this integer value here, you turn the 2-argument function into a single argument function. So although this may look a little bit strange at first, I hope that you can now see that by exploring partial function application, how this notation reflects a 2-argument function, and that when you add an actual when you supply an actual value for one of the arguments, that what you get is a single argument function. Next up, Anonymous Methods Part 3. Thank you for listening.